thermal fluid sciences experts. This is ProReadyEngineer.
Mass flow rate, very important for us. That's not the property, but it's extremely important quantity. M dot. You see, M dot, as it implies, is mass flow rate. Just think about the definition for a second. Mass rate, the rate by which the mass is moving. So when I tell you that your, the jet engine has 300 kilogram per second flow rate. 300 kilogram every second, 300 kilogram of air, right? That you start relating mass flow rate. You see, these devices here, you go from just a gasoline injector, this teeny tiny, and then you go to a gas furnace like the one that sits in your own home, to a car engine, to a diesel engine a little bit bigger, to the boiler. You see this thing sitting back there is a boiler sitting back there. Look at the size, tremendous. Boilers are very large. Jet engine, steam turbine, and rocket. Then, really at the end of the rocket. Take a look at the numbers here. See the rockets. 13,000 kilogram per second. You see, imagine you are an engineering student. You are solving a problem for this jet engine. You are calculating the airflow rate and you finished your problem, and then you said m dot air is 1 kilogram per second. This is an engine that is flying an aircraft that is 787, and you are telling your professor or the person who is checking on you, are you an engineer or not, 1 kilogram per, what is 1 kilogram per second? I can get some tomato, a bag of tomato that is 1 kilogram, and you're sitting here, and each second I throw 1 kilogram at you. That's the tomatoes, 1 kilogram, and you'll be able to pick it. It's going to be a little bit heavy, but just 1 kilogram per second. Every second I throw on you. How do you think that the jet engine that you see in the movies, the very large, all the things, but when you see the cars, when the couple videos that show when the car goes behind it with the jet coming out, it flips a car, it flips a truck, it flips, right? So it cannot be 1 kilogram per second because you don't have a feel for it, right? To the very small, like the gasoline injector in your car, this very small, teeny tiny injector is in grams per second. Very small amount, grams per second. And this makes sense. Imagine you are solving a problem for your gasoline car, right? And you're giving your professor the estimate. You tell him, when I estimated the amount of fuel per injector, it is 5 gallons per second, right? Think about that now. Sit and think. 5 gallons. Every second your car is running. One injector takes 5 gallons. You have no engineering sense. There's no engineering sense there. That number has to be an extremely small number. The car runs for days with just 17 gallons for days, right? There's no engineering sense. So very important to have engineering sense. M dot is the mass per unit time. Units can be kilogram per second, kilogram per hour, power per second, power per hour, right? Depends on the units you are using. Build a feel for it. M dot is calculated by multiplying rho A times V. It's a very famous formula. When you want to calculate the mass flow rate, you take the density, multiply by the cross-sectional area, multiply by the velocity perpendicular to that area. This is very important formula, very simple, very important. Take care of the units. This is kilogram per second, kilogram per meter cubed, meter squared, and meter per second, right? This is very important. If I give you 3, you get the 4th. Any 3 of these, you get the 4th one, right? Very good. So now we know what is mass flow rate. We know mass flow rate is important. Let's move to measurement of mass flow rate. So it's important. We need to know how much fuel we are burning. We need to know how much the aircraft is burning fuel per unit time. We need to know the number. We can use it in engineering design, calculations. So how do we measure it? Well, there's direct measurement, and one of the most famous and most accurate device in measuring mass flow rate is Coriolis flow meter. It looks something like that, not necessarily Don't let this schematic fool you. So when you walk in a test cell, for example, or an industrial facility, if you don't see that U-shaped, you say, oh, that's not, no. Sometimes it is actually U-shaped, but it's covered. It's contained in a cover, so you cannot see that U-shaped. But it is, when you remove the cover, you will, see something under it that looks like that. So that's Coriolis flow meter. I'm not going to go over here how it operates or any of that. Again, as I'm doing today, I'm just telling you the name of the device so you know, and that it's very accurate. So one day you are working somewhere as an engineer, they tell you, hey, we want to measure the mass flow of this fuel we are pumping. And you tell them, let's get a Coriolis flow meter. Then they tell you, oh, that's Coriolis is very expensive. It's very expensive, most expensive thing we can bring for that. You say, well, because it's the most accurate. It's going to be very accurate. Give us the accuracy that we need. So that's what I'm trying to communicate to you. That's a direct measurement. Now, indirect measurement for mass flow rate, very common, very famous are the orifices, the Venturi, sonic meters. They all indirectly, through pressure measurement and temperature measurement, density, and things of this nature. I'm not trying to cover that here, but just want you to know you can use these. They are much cheaper devices, but not as accurate as the Coriolis, except the Venturi. There is the turbine flow meter, and this essentially looks like a turbine that spins, and the spin rate relates to the velocity, knowing the area. Again, indirect measurement of the flow. And the ultrasonic flow meter, where you have a transducer and a transmitter and a transducer, and then essentially you correlate this ultrasound as it goes through the fluid, and you translate that into a mass flow rate. Just want you to know some name of these devices.